Hi everyone, welcome back. So in this video, we're going to do an analysis of a non-inverting op-amp. All right, as you see here on the left. So what we're going to do is we're going to come up with we're going to derive expressions for VO, that's V out or voltage out, and also an expression for AV, which is voltage gain. All right. So as per usual, before we proceed, I just want to remind you guys of the two ideal op-amp assumptions we always make when we're analyzing a circuit with op-amps. Number one is that there'll be no currents going into either terminals, either the inverting or the non-inverting terminal. So both I1 and I2 will be 0 amps. And the other is that both the voltages on both nodes will track each other, right? So whatever V2 will be whatever V1 is going to be. So if you set an expression for V1, that's what V2 is going to be. If you set an expression for V2, that's what V1 is going to be. All right. So let's start with, as always, labeling our currents and voltages before we do our analysis. The first thing I want to label is the current that is flowing from right to left of RF. Right. So it's a current that flows through RF from right to left. So that current is going to flow, and when it gets to the junction here, none will go into the inverting terminal because of the first assumption. So that means all of IF will completely flow through Rn. So therefore I'm going to put in another IF, the same amount of current, will then flow through Rn. Now because we define currents as moving from right to left, so therefore the voltages of RF is going to be pointing to the right, and the voltage across Rn will also be pointing to the right, meaning that we're saying that the right side will be at a higher potential than the tail side, the left side. All right. So that's about currents. And now, because of the second assumption, we can assume that since the non-inverting terminal is called Vi, so therefore we can say that the inverting terminal is also Vi. So we're going to label that as Vi. All right. Okay, so that's based on the second assumption. So now we can start writing some expressions for our circuit. So current through RF, all right, is going to simply becomes IF. That's IF, all right. IF is equal to, well, okay, it's the voltage. I equals V over R, so it's voltage over resistance. So if we look at the right side of RF, that's V0, and the left side of RF is VI. So we just say VO minus VI. All right, so that's going to be the voltage across RF. So divided by, of course, RF. All right, so that's our expression for IF, and then the other one is current through Rn. All right, so that's going to be IF. Again, it's IF, right? And again, the voltage is basically from the right, the right side minus the left side. So that's going to be Vi minus 0 divided by Rn. All right, so once we have these two equations, we can then equate the two, right? Equating IF for both RF and Rn. So what do we have? What will we have? Well, we're going to have on the left side. So let's say the left side is RF, the RF expression. So we can write VO. So I'll put that in bracket. VO minus VI divided by RF is going to be equal to the IF that's gone through Rn, which is, well, Vi minus 0 is Vi, so I'll just write Vi divided by Rn. All right, so, well, we have to expand the left side into a VO over RF minus Vi over RF to split that out, so let's do that. So that's VO over RF minus Vi over RF. All that is going to be equal to just the whatever's on the right hand side, so Rn. All right, so that's how we expand it, and then we can collect the VI's together. So I'm going to push the minus VI over RF across to the right hand side of the equal sign, so that on the left side it will just be VO. VO divided by RF is going to be equal to, well, the original VI over Rn, and then plus this term, the minus VI over RF is gone to the other side, so it becomes plus VI over RF. All right, and next we simply factor out VI because VI is on both sides. So the left side will remain for now. All right, so equals to, well, VI is going to be outside, so I'm going to factor out VI. And then in the bracket will be 1 over Rn plus 1 over RF. Oops. All right. So that's what's going to be. Okay, so now finally we just simply take RF and put it across to the other side so that you just have VO by itself. All right, so VO is going to equal to, okay, so I'm going to put the RF inside, I'm going to multiply inside the bracket, all right? So the outside the bracket will remain our VI, but inside the bracket will be RF over Rn, sorry, all right, plus RF over RF, all right? Okay, so, and so the final simplification is basically VO is going to be equals to VI, and I'm just going to turn the other way around. So it just becomes, because RF over RF is just 1, right? So that cancels top and bottom, becomes 1. So I'm just putting it on the front, on the left side, because I think in most books this is how they would write it. Of course, it's the same thing. Just make sure it's familiar for you guys. All right, that's it. That's our expression for VO. All right, that's our expression for VO. The term 1 plus RF over Rn is basically called the gain, right? It's called the gain, the voltage gain. So to get expression for AV, all I have to do is just put VI back to the left side for us to get an AV. All right, so let's do that. So AV, which is equals to VO over VI, is simply going to become 1 plus Rn over Rn. And that's how you derive the expression for VO for a non-inverting op amp. All right? So see you guys in the next video.